The last two patterns ran on credit. Binary search threw away 500 million elements with one comparison, and the license was a single word: sorted. The converging pair retired an element per comparison, same license. Both times, the sorted array just appeared. Nobody asked what it cost. Today, the bill comes due, because sorted data does not exist in nature. Logs arrive in arrival order. Users sign up in sign-up order. Every sorted array in production was paid for by a sort, which makes sorting the purchase that funds half of this course and the most studied problem in computer science. So we're buying sortedness three ways. First, merge sort, the cleanest recursive algorithm ever written, and last lesson's call stack does the heavy lifting. Then Quicksort, faster in practice, carrying a famous catastrophe. And then we open your standard library and find out what it actually runs. Spoiler, not the textbook. Nobody ships the textbook. Start on the bottom shelf, the quadratic sorts, because one of them refuses to die. Selection sort is the obvious idea. Scan everything, find the smallest, swap it to the front. Scan the rest, find the next smallest. In scans over a shrinking array, that's the order in squared triangle from lesson 1, and it has no redeeming features. Insertion sort is the card player's idea. Take the next element and slide it left past everything bigger until it sits in place. Still order in squared, worst case, but look at its virtues. If the input is already nearly sorted, each slide is a step or two, and the whole sort runs in nearly order in. It never reorders equal elements. Hold that thought, it gets a name later. And every move touches immediate neighbors, which is exactly the access pattern lesson 2 crowned. A few dozen elements is 2 or 3 cache lines, and insertion sort just slides them around inside L1. Bubble sort, the one everyone learns first. Adjacent swaps, same in squared, none of those virtues. It lives in courses, not in libraries. And the shelf's price at scale? 1 million elements, order in squared, 2.8 hours. Fine for a hand of cards. Dead past that. So how do you sort 1 million elements in a fraction of a second? Last lesson handed you the exact tool. To write a recursive function, you design the base case, and one step, written as if the recursive call already works. Apply the leap of faith to sorting. Base case. An array of one element is already sorted. Nothing to do. The step? Split the array in half. Trust the recursion to hand you back each half, sorted. That's the leap. Then your only real job is the combine. Turn 2 sorted halves into one sorted whole. That's merge sort. John von Neumann worked it out in 1945 for one of the first stored program computers ever built. And before we run it, price the shape, because lesson 9 taught you how. The problem shrinks by half per call. That's the friendly kind of recursion. Depth log in, about 20 frames for 1 million elements. Harmless. So everything, the entire algorithm, now rides on one question. How cheap is it to merge 2 sorted halves? Here are 2 sorted halves, 3, 27, 38, 43, and 5, 9, 10, 82. Put a pointer on the front of each. Lesson 7 taught the question to ask, is there a reason a pointer never needs to go back? Here's the reason. Each half is sorted, so the element under each pointer is the smallest thing left in its half. Now compare the 2 pointers. The smaller one is smaller than everything left in its own half, and smaller than everything in the other half too, because it just beat that half's front. It is the minimum of everything remaining, so it's final. Write it to the output, advance that pointer, never look back. Watch. 3 versus 5. 3 goes out. 27 versus 5. 5. 27 versus 9. 9. Then 10. Then 27. 38. 43. And the left half empties. Copy the 82 across. Done. 8 elements, 7 comparisons, 1 pass. Merging is order n. The combine step is cheap, and that one fact makes the whole algorithm work. Now run the whole thing on 8 elements and watch the shape. 38, 27, 43, 3, 9, 82, 10, 5. Split. 2 fours. Split again. 4 pairs. Once more. 8 singles, and a single is the base case. Sorted by definition. Notice, just like factorial, the trip down did no work at all. Everything happens on the unwind, and the unwind merges. The pairs merge. 27, 38, 3, 43, 9, 82, 5, 10. The fours merge. 3, 27, 38, 43, 5, 9, 10, 82. And the final merge, the one you just watched, produces the answer. Now count, because this is the whole lesson. 8 halves down to 1 in 3 doublings, log n levels. And at every level, each of the 8 elements passes through exactly 1 merge, n work per level. N work times log n levels. Order n log n. That's the rung from Lesson 1's ladder, the one labeled have and recombine. Derived, not asserted. 1,000,000 elements, 20 levels, 20 million moves, a fraction of a second. The 2.8 hours just became 0.2 seconds, and you watched every move that did it. Merge sort's price tag deserves a careful read. The guarantee first. Order in log n in the worst case. No luck involved, no assumptions. The merge does the same work whether the input arrived shuffled, sorted, or chosen by an enemy. The cost. The merge needs somewhere to write, so merge sort carries order in extra space, a scratch buffer the size of the input. That's the trade. It also keeps equal elements in their original order, which sounds like trivia and decides real library designs. A few minutes, and it gets its name. And 2 quiet properties do serious work in production. The merge reads both halves front to back, writes front to back. 3 sequential streams. Lesson 2 told you what the prefetcher does with that. And merging never jumps, never needs random access, which makes it the sort for data you can't index into. Linked lists. The Linux kernel sorts its lists with a file literally called list sort. It's a merge sort. And data too big for memory? Entirely. Sort what fits. Write sorted runs to disk, then merge the runs as streams. Every database that has ever spilled an order by to disk is running this scene. The second champion starts from the opposite end. Merge sort does all its work after the recursion, combining. Quicksort does all its work before. Pick an element, call it the pivot. Then partition. Rearrange the array so everything smaller than the pivot sits to its left, everything bigger to its right. The pivot itself lands in its final sorted position, done forever. Then recurse on the 2 sides, and there's no combine step at all. Watch 1. 7, 2, 9, 4, 3, 8, 6, 5. Pivot, the last element, 5. And look at the shape of this scan. It's Lesson 7's reader-writer geometry. A reader visits every element. A writer marks the end of the small zone. The reader finds the 2. Smaller than 5? Swap it back to the writer. The 9? Bigger. Leave it. The 4? Swapped back. The 3? Swapped back. Reader's done. Swap the pivot to the boundary and read the array. 2, 4, 3, 5, 9, 8, 7, 6. 5 is exactly where the final answer needs it. 1 pass, order in place. This scheme is Lemuto's, the easiest to follow. Real libraries descend from Hoare's original, which closes in from both ends. Same idea, fewer swaps. Now recurse. The left side, 2, 4, 3. The right side, 9, 8, 7, 6. Each side picks its own pivot, partitions, recursives, and single elements in it. If the pivots land near the middle, the arithmetic is merge sorts all over again. Have the problem, log in levels. In partition work per level. Order in, log in. A random pivot delivers exactly that in expectation. But here's why Quicksort wins the benchmarks. No scratch buffer. The partition rearranges in place, so the only memory bill is the stack, and having recursion means order log in frames. No merge pass writing everything out and copying it back. Just one hot loop, comparing against a pivot that sits in a register, scanning forward through the array, which is the exact pattern the prefetcher rewards. Done well, Quicksort is the fastest comparison sort on real hardware, and it is not particularly close. Done well. Because everything I just said leaned on 3 words. Near the middle.
Feed it the one input nobody expects to be dangerous. An array that is already sorted.
1 through 8. Pivot the last element. 8. The partition scans and everything is smaller than 8. The entire array lands in the small zone. The big zone is empty. The pivot was already in its final position, and the recursion gets back everything except one element, which pivots on 7 and peels off 1 more, then 6. Shrink by 1 per call. Lesson 9 named this the dangerous kind. Depth n, not log n. 100,000 sorted elements is 100,000 stack frames. On most platforms, that's a crash before it's even slow. And the comparison count, n plus n minus 1 plus n minus 2, the quadratic triangle. The fast sort, handed the easiest input imaginable, degrades to the bottom shelf and blows the stack on the way down. And sorted, nearly sorted input is everywhere in production. Yesterday's sorted file plus today's appends. A resort after one edit. A sort that dies on sorted data cannot ship as is. Every production quicksort is a defense against that scene. Defense 1. Stop being predictable. Pick the pivot at random, and no fixed input is dangerous anymore. The catastrophe now needs bad luck at every level, and those odds vanish. Expected order in log in on any input. Defense 2. Median of 3. Look at the first, middle, and last elements. Take the middle value. Sorted input now picks the true middle, perfect pivots. Defense 3, the clever one. Give up on a timer. Musser's introsort, 1997, runs Quicksort while counting the recursion depth. Past about 2 log-in levels, the pivots have provably gone wrong. So it stops and hands the rest to heapsort. Guaranteed in log-in, no luck required. We build the heap in Lesson 15. For now, it's the insurance policy in the basement. One more thing, because attackers read papers. McElroy published a killer adversary for Quicksort, a recipe that constructs on the fly an input forcing a known implementation toward its worst case. Sorting attackers supply data with a predictable quicksort is a denial of service waiting to happen. So randomize, or carry insurance. Real libraries do both. Before we open those libraries, an honest question. Both champions landed on order n log n. Coincidence? Could some undiscovered algorithm sort with comparisons in order n? No, and the argument is short enough to keep. 8 distinct elements can arrive in any of 8 factorial orders, about 40,000. A correct sort must handle all of them, and each different arrival order needs a different set of moves to fix it. Now, the only tool a comparison sort has is a yes or no question. Is A less than B? One comparison can, at the very best, split the possibilities in half. So, how many halvings to pin down one ordering out of 40,000? Log of 8 factorial. About 16 comparisons, minimum, worst case, for any comparison sort that could ever exist. And in general, log of n factorial grows like n log n. That's the floor. It's why Lesson 1's ladder calls in log in good sorting. Full stop, not a waypoint. One honest footnote. Sorts that don't compare, counting sort, radix sort, exploit the structure of the keys themselves and can hit order in on the right data. Outside this course's part 1. For comparisons, the plateau is the law. One promise from the merge sort price tag is still open. The name. A sort is stable if elements that compare equal keep their original order. Sounds like trivia. Here's the real case. An employee table, sorted by name. Anna, Bo, Carla, Dev. Now sort it by department. Anna and Carla are both in sales. On department, they compare equal. A stable sort keeps Anna before Carla because she was before Carla coming in. So watch what composes. Sort by name, then stable sort by department. You get departments grouped and names alphabetical inside each one. Two sorts stack into exactly what a human wants. An unstable sort scrambles the names inside each group, and the first sort was wasted work. Now grade the champions. Merge sort, stable for free. When the 2 pointers tie, take the left one. That's the entire implementation. Quicksort, not stable, and it can't cheaply be. You watch the partition fling that 7 from one end of the zone to the middle in a single swap. Long-distance swaps trample the order of equals. That one difference is why your language ships 2 sorts, and why the default is usually the stable one. Which brings us, finally, to what your language actually runs. 2002. Tim Peters, a Python core developer, looks at what Python programs actually sort, and notices it is almost never random. Logs are nearly sorted. Files arrive in sorted chunks. Somebody appended to a sorted list. So he builds a merge sort that exploits that. Timsort walks the array hunting for runs, stretches that are already sorted. Found the descending run, reverse it in place. Runes shorter than about 32 elements get extended with insertion sort. There it is. Then it merges the runs, carefully with a trick called galloping that leaps ahead in growing jumps when one run keeps winning. On random data, a solid, stable in-log-in merge sort. On real data with structure, it approaches order in. Fully sorted input is one run detected in a single pass. Timsort has been Python's list.sort for over 20 years. Java adopted it for objects, and in 2018 it became JavaScript's array sort too. Before that, V8 quicksorted any array longer than 10 elements, unstably. A generation of front-end developers learned the word stable from bug reports about reordered table rows. The other family tree grows from Quicksort. C++'s standard sort is Musser's introsort. Defended pivots, the depth counter, heapsort insurance, and insertion sort below 16 elements. Rust's unstable sort and Go's modern sort ship descendants of pattern-defeating Quicksort, an introsort that also detects patterns. Already sorted input, order in. All equal elements, order in. An adversary bending the pivots trips the fallback. Go's older sort, .sort, and newer slices, .sort, run the same family. The generic one just pays less per comparison. Now step back. Every library on that list makes the same 3 moves. A fast workhorse, Quicksort family, or merge family where stability is promised. Pattern detection, because production data has structure. And insertion sort at the bottom. Every single time. That last one is a debt this course took out in Lesson 1. The oddity. Why do real libraries hand small slices to a quadratic sort? Lesson 2 paid the why. 2 or 3 cache lines, sliding neighbors inside L1. Here's the where. Inside every sort your code has ever called. The textbook is the skeleton. The engineering is everything wrapped around it. So sortedness is paid for, and the receipts are readable. Merge sort trusts both halves and earns everything in the merge. Guaranteed in login,
stable, costs a buffer, sort streams and lists and disks. Quicksort earns everything in the partition. In place, fastest in practice, lethal without a defended pivot. The floor is in login because comparisons only have, and the libraries ship hybrids. Detection on top, insurance underneath, insertion sort in the small slices. But look at what both champions actually did. Split the problem, solve the pieces by recursion, combine. Merge sort combines after, quicksort partitions before. And the arithmetic came out identical both times. Log in levels, in work per level. That move is bigger than sorting. It has a name, divide and conquer, and a general theory that prices every algorithm shaped like this, including ones we haven't met. How to split, when it pays, and how to read the cost straight off the shape of the recursion. That's next.